Lab 5, Choose Your Own Adventure, by Norwood Dennis. In this lab, I observed the motion of a steel ball bearing as it fell from a height of approximately 1.8 meters above the ground. Using Tracker, I analyzed this video play here, of the bearing falling from a height of 1.8 meters. The fundamental principle tells us that Newton's second law says that the final velocity is equal to the initial velocity plus the quotient of the net force over the mass of the object multiplied by the change in time. From simply observing the increasing amount of space between the point masses in each frame of the tracker data, we can tell that the bearing is increasing in velocity and therefore the final velocity will not equal the initial velocity. AKA, if the change in velocity isn't zero, then the net force cannot be equal to zero, because we know that the only agents exerting a force on the ball would be the earth and the air. We can deduce that the net force is equal to the weight force, which is negative mg j hat, plus the drag force, which is the proportionality constant for the magnitude of the drag force times the velocity of the ball at that instant. So if we look at the tracker video here, we can see the increasing space in between the point masses in each frame. And here you can see the change in y position over time, which is also shown as a table to the right. If we go to the next slide, we can see this graph in better detail. So you see that it falls for approximately 0.42 seconds and falls a bit over 1.8 meters. So there's the table of the y positions with respect to delta t, and here we see those formulas, or the initializations that are necessary for the formulas that we were discussing earlier. The variable b, which we can see here at the bottom, is the proportionality constant for the magnitude of the drag force. So it was found through trial and error in an attempt to get a final y value in the VPython module as close to that found in Tracker. So I would run the module with a value of b, and the closer I got to the final y position observed in Tracker, the more accurate value for b it would be. So the closest I got to the final y position in Tracker, which was negative 0.863 meters, the closest I could get to it with the value of b equaling 0.19 gave me a final y position of negative 0.8 meters, which was fairly close, but interestingly enough not as close to the final y position that we would find if we did not include the drag force at all, which we'll discuss later. So if we run this Python, we can see this yellow arrow, which is proportional using the arrow scale 7.4. So the yellow arrow is the weight force, while the blue arrow is proportional drag force, which we can see is pretty minimal compared to the weight force. So if we look at the graphs of the Tracker observed data versus the predicted data from the VPython module, we can see that they are fairly similar, although the Tracker data has a somewhat different curve to it, and if we can see somewhere between 0.25 and 0.3 seconds, there is a bit of a gap, which I think is from the an error in the tracker frames. But in conclusion, as compared to my findings from Lab 2, in which I analyzed the motion of a wad of paper as it fell to the earth, the effect of drag on the ball bearing in this lab was much less noticeable than in the paper experiment. I think this is most likely due to the fact that the wad of paper was both less dense and had greater surface area than the steel ball. And to be more specific, I think in more technical terms it's referred to the skin friction between the surface of the object and the fluid through which it's moving. In this case, that'd just be the air. As well as the form drag, which is determined by the shape of the object moving through the fluid in its cross-sectional area. So if you think about the shape of a crumpled wad of paper versus the more streamlined shape of a ball bearing, it makes sense that the ball bearing would have less skin friction as well as less form drag. And to continue conclusions, if the drag force was not taken into account, and that is I just set b to 0 in Python, then we'll find that the final y value is negative 0.88 meters, which is a bit farther than the bearing traveled in the y direction that we observed in tracker, approximately 0.02 meters farther in the y direction, which is strange because when the closest we could get to the final y position using a drag force constant, proportionality constant, was negative 0.07 meters, which is about 0.06 meters less accurate than what we found in tracker, and therefore less accurate than if we had not included this proportionality constant. So from that, I feel like I can conclude that the effect of drag on the ball bearing is so minimal that it's more accurate to not include B in calculating the motion of the ball bearing in Python. And that's it. Thank you for watching.